In part 4 of the Unit 10 notes, we are going to be covering the ideal gas law, Dalton's law of partial pressure, and Graham's law. The ideal gas law was first stated by Bonnet Paul Emile Clapeyron in 1834 as a combination of the other gas laws. In this law, we are given two new variables. The N represents the number of moles of gas, and the R is the ideal gas constant, which depends on the unit of pressure being used. Now, we have used a number of different types of units. We've used atmospheres, kPa, torr, millimeters of mercury, psi, but to simplify things a little bit, whenever you have an ideal gas law problem, I will only use one of two units of pressure. They will be in either atmospheres or kPa. So you'll have a 50-50 shot of picking the correct gas law constant. And these are not numbers that you would have to memorize. You will be given these numbers. If you are given a pressure which is in atmospheres, you should use this gas law constant. So 0.0821 liters times atmospheres over moles Kelvin. If you're given a pressure unit which is in kilopascals, you would use 8.31 liters times kPa over moles Kelvin. In our first ideal gas law problem, we have a deep underground cavern which contains 2.24 times 10 to the 6th liters of methane gas at a pressure of 1.50 times 10 to the 3rd kPa and a temperature of 42 degrees Celsius. How many moles of methane gas does the cavern contain? All right, in order to solve this problem, we're going to write out each of our variables. So we have P, V, N, R, and T. Our pressure is 1.50 times 10 to the 3rd kPa. Our volume is 2.24 times 10 to the 6th liters. Our moles is unknown, so that's question mark. Our temperature was 42 degrees Celsius, but we know at this point that we're never allowed to use Celsius for any gas law problem. So I'm going to add 273 to that, and it's going to come out to 315 Kelvin. Now for the gas law constant, I need to pick out the one that is appropriate based on my pressure unit, and I have kPa here. So that means I need to pick this one. So I'm going to plug in 8.31 liters times kPa over moles Kelvin. And yes, you do need to write out all of these units. All right, our next step. We always identify the law that's being used, and then we move the variables around if needed. We have PV equals nRT, and we want the N by itself. So that means dividing both sides by R and T. So I now have a new version of the equation. N equals PV over RT. I'm going to plug everything in. My pressure is 1.50 times 10 to the 3rd kPa. My volume is 2.24 times 10 to the 6th liters. My gas law constant is 8.31 liters times kPa over moles Kelvin. And my temperature is 315 Kelvin. All right, now this is the reason why it was important that you actually wrote out all of these units. I can see that my kPa is going to cancel top and bottom, so does liters. My Kelvin cancels. I am left with 1 over moles, which is equivalent to moles. So I know that everything is in the correct place. From here, I am going to multiply across the top and divide by each of these two bottom numbers individually. The way that I typically plug this into a calculator, I multiply, I press enter or equals. Then I divide by one of them. I press enter or equals, and then I divide by the other. There are other methods, but you're less likely to make mistakes if you do it that way. If you multiply and divide across here, you end up with 1.28 times 10 to the 6th, and that is going to be moles. That is our moles of methane gas. In our second ideal gas law problem, we are trying to determine the temperature of 2.49 moles of carbon dioxide gas contained in a 1.00 liter vessel at a pressure of 1.41 atmospheres. So just like before, P, V, N, R, and T, I'm writing out each of my variables. My pressure is equal to 1.41 atmospheres. My volume is 1.00 liters. My moles is 2.49. My temperature is unknown. My R value this time, because I was given a pressure in atmospheres, I need to use this one. All right, now we're going to write out our law. We have PV equals nRT. This time we are solving for temperature, which means we need to divide by N and R. Temperature is equal to pressure times volume over moles times the gas law constant. My pressure was 1.41 atmospheres. My volume is 1.00 liters. My number of moles is 2.49. And my gas law constant is 0.0821. And I'm going to write in each of my units here. Atmospheres cancels with atmospheres, liters with liters, moles with moles. I'm left with Kelvin. So my temperature here is not in Celsius, it's going to come out in Kelvin. We have 6.90, I'm rounding for 3 significant figures, Kelvin. And if you're familiar with the Kelvin scale, you should recognize that this is incredibly cold. Kelvin goes down to 0 Kelvin, which is actually absolute zero, so this is very close to that. All right, so a little bit more information about ideal gases versus what we call real gases. An ideal gas is one that follows the gas laws at all conditions of temperature and pressure. To do so, the gas would need to occupy 0 volume and would need to exhibit no attractive forces towards other molecules or the walls of their containers. Since neither of those conditions can be true, no gas is truly ideal. So no gas is going to fit our laws exactly. But under certain conditions, we can make our laws, or the math, work out very, very close. A real gas is a gas that does not behave according to the assumptions of kinetic molecular theory. Fortunately, at the conditions of temperature and pressure that are normally encountered in a laboratory, real gases tend to behave very much like ideal gases. So here we have a checkpoint question. Under what conditions do you think real gases are to behave more like ideal gases? So our ideal gases can't interact with each other and they can't have any kind of attractive force to the outside of their container. Now, if our gas molecules were moving fast enough, they wouldn't really have time in order to feel those attractions. The same is true if our gas molecules were really separated or were far apart from one another. So conditions that would apply here would be high temperature, because our molecules are moving so quickly that they're not really able to interact with each other, or if we have a large volume. It's important to understand this because when we're working with gases at really low temperatures, or maybe volumes that are quite small compared to the relative amount of gas inside, those are the conditions where our gas laws are not going to work very well. So as long as our temperature is relatively high or our volume is relatively large, our laws are going to work just fine. Next up, we have Dalton's law of partial pressure. In 1801, John Dalton developed Dalton's law of partial pressure, in which he described the relationship between the total pressure in a container and the individual pressures applied by each gas. The partial pressure of a gas is indicated by a P with a subscript that is the symbol or the formula of that gas. So for example, the partial pressure of nitrogen would be Pn2. Here in this diagram, we can see the pressure exerted by an unknown element or compound labeled as P1. So this is exerting a pressure of 1 atmosphere. We have a separate container where the pressure of some unknown element 2 is exerting 2 atmospheres of pressure. What this law is stating is that if I combine these two gases, those pressures are going to be cumulative. So now, since all of these gas molecules are within the same space, instead of 1 or 2, we have a total of 3 atmospheres worth of pressure. In terms of a formula, you can see this in a couple of different ways. Your total is equal to the pressure of each of the individual gases. Now this dot 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 at the end is because there is no set limit to how many gases might be in your container. Maybe you only have 2, maybe you have 3, or maybe you have an infinite number of gases within some kind of area. You could also rearrange this to solve for any of the particular variables on the right side. So here you can see that I solved for pressure 1. So maybe I wanted to know how much pressure was given off by just that particular gas, and I knew the total pressure of the container and the pressure of all the other gases. So now we're going to go through a couple of examples where we solve Dalton's law problems. Here we are calculating the partial pressure of neon in a flask which has a total pressure of 1.87 atmospheres, and the pressure of krypton and helium is 0.77 and 0.62. So this is a fairly simple problem. I know that my total is the 1.87, and I know that 2 of my pressures are 0.77 and 0.62. So all I have to do is take 1.87 atmospheres, and I'm going to subtract away the other 2 gases. So I'm going to subtract 0.77 atmospheres, and I'm also going to subtract 0.62 atmospheres. So here that means that the partial pressure of my neon, which I could abbreviate as PNE, is going to be equal to 0.48 atmospheres. Air contains oxygen, nitrogen, carbon dioxide, and trace amounts of other gases. What is the partial pressure of O2 at 101.30 kPa of total pressure if the partial pressures of N2, CO2, and the other gases are 79.10, 0.040, and 0.94? So this is very similar to the previous problem. I want to try to find the partial pressure of my oxygen. So I know my total amount of pressure was 101.30 kPa, and I'm going to subtract away all of the other pressures. So 79.10, 0.040, I should have my units here, kPa, kPa, and 0.94. So that is going to come out to 22.22 kPa. Now clearly this is a pretty simple type of question. It's really just addition or subtraction. So be aware of the units that I am using for pressure. In the past, in some of the practice problems, I might have maybe one of the units of pressure is in atmospheres and the other one is in kPa, and you have to do a little conversion first before you can add or subtract them. So within all of our problems, if you have different pressures, you should make sure that the units are compatible before you do any kind of mathematical operations. All right, next up, we are on Graham's law. When a person opens a bottle of perfume in one corner of a large room, the scent spreads throughout the entire room. Diffusion is the tendency of molecules to move from high to low concentration until the concentration is uniform. While gases diffuse rather quickly, liquids diffuse more slowly, solids essentially do not diffuse. So in this diagram, we can see a container which is separated in the middle. On one side we have the hydrogen gas, and the other side we have the oxygen. When you open up the barrier between them, they will slowly go back and forth until we reach what we call equilibrium, where the gases are equally distributed on both sides. There is also a process known as effusion. This process is of a confined gas escaping through a tiny hole in its container. Effusion can be observed by the fact that a helium-filled balloon will stop floating and sink to the floor after a day or so. So we have this filled balloon here, and over time, gas molecules will begin to escape and it will become deflated. You can also see that within this diagram here. So Here we have this tiny little pinhole in both of these containers. The helium, because helium is a smaller atom, it's able to pass through the pinhole a little bit more easily. But if I have a larger or more complex gas molecule, it might take longer for it to eventually pass through that pinhole. So based on this, we can see that smaller atoms or molecules are going to be able to effuse quicker than larger ones. In 1848, Thomas Graham developed Graham's law, which states that the rate of effusion for a gas is inversely proportional to the square root of its molar mass. The rate of diffusion also depends on the mass of the gas particles. Gases of lower molar masses diffuse and effuse faster than those of a higher mass. There are equations which can be used to describe the phenomenon. You can see one of them right here, but you are not going to need to perform these calculations in class. So for our purposes, to keep things as simple as possible, you really just need to know that a smaller molecule will effuse and diffuse faster than a larger one. Which brings us to a checkpoint question. Which gas would effuse faster, neon or carbon dioxide? Now, in order to solve this type of question, what you want to do is compare the molar masses of this atom and this molecule. Neon is on the periodic table, so I can look that up. It has a molar mass of 20.18 grams per mole. Carbon dioxide, well, the carbon is 12.01, and then each of the oxygens is 16.00, and there's two of them. So that gives you a total molar mass of 44.01. Since neon has a lower molar mass, it would effuse and diffuse faster. So neon would be our answer to this question. So for our class, we're not going to be comparing the actual rates, but I might ask you which one would diffuse or effuse faster. That is the conclusion of your Unit 10 notes. If we continue on here, I just want to remind you that you should be completing all of the practice assignments on KIA prior to our formal assessment. If you do particularly poorly on any of the practice assignments, it is your responsibility to ask questions so that you can improve. On many of the gas law practice assignments, I have also embedded Tyler DeWitt tutorial videos which you could use if you need additional help. For the labs for this unit, we have our Graphene Gas Laws lab, the Rocket Lab, and any of the other labs that might have been posted to Google Classroom. If there's any content from a lab that you do not understand, again, it is your responsibility to ask questions. You may ask for help during our independent practice time in class or before or after class. Finally, YouTube. So as we've had with our other units, I've compiled a list of resources from other popular YouTube channels and put them into our playlist on my YouTube channel. So for Unit 10, there are videos from Tyler DeWitt, and since this is a very calculation-heavy unit, I do highly recommend his videos. There are also some videos from Melissa Maribel, which are also very good. Crash Course is good for the general content of gas laws, like how everything works, but if you need help with the calculations, you're better off looking at these two channels. And of course, you also have TED Ed.